Brooks theorem and color critical graph. Recap of previous lecture, we have discussed k coloring of graph, optimal coloring, click number, Cartesian product of a graph, upper bounds in terms of colorings, that is upper bounds of greedy coloring algorithm. Then we have also covered the greedy coloring when the graph is interval graph, and such kind of graphs basically arises in the problems of register allocation application in compiler design. Content of this lecture we will discuss the Brooks theorem, which will give the bound on the chromatic number of a graph, and we will see the proofs of it. Then we will also look into the k critical graphs. So, k critical graph here means that k color critical graphs. Brooks theorem, let us see the background of the Brooks theorem before we state this particular theorem. The bound of a chromatic number in a graph is given by 1 plus maximum degree of a graph. Now, this particular bound we have earlier stated. So, let us see that what are the graphs when this bound will become equal. So, that equality will hold for the complete graphs and the odd cycles. So, for complete graphs and odd cycle, chi of g is less than or equal to 1 plus maximum degree of a graph for complete graphs and odd cycle. So, this is one point. Now, by choosing the vertex ordering more carefully, we can show that these are essentially the only such graphs where this equality in this particular bound will hold. If the graph is, this implies, for example, the Peterson graph is 3 colorable without finding an explicit coloring. To avoid unimportant complication, we state that the graphs are connected graphs. For disconnected, we can also extend it for finding out the chromatic number of the components and take the maximum of it. That becomes, so without loss of generality, we will consider only the cases for connected graphs. So, it extends to all the graphs because chromatic number of a graph is the minimum or a maximum chromatic number of its components. So, that I have already stated. We will see the proof by of the Brooks theorem given by Lowas in 1975. So, the Brooks theorem is stated as under, which is given in 1941, and the proof we will give by Lowas in 1975. So, if graph G is connected graph other than the complete and odd cycle, for complete and odd cycle, this chi of G is 1 plus for complete graph and odd cycles. So, if the graph is not complete other than the complete graph, then the Brooks theorem says that the chromatic number of a graph G is less than or equal to the maximum degree of a graph. Let us see the proof given by Lowas. Let G be a connected graph, and this particular symbol k, small k, we are using for the maximum degree of a graph G, which we have considered in our discussion. We may also assume that the maximum degree of a graph should be 3 or more in our discussion. Why? Because if it is less than that, then it becomes a complete graph or the odd cycle, and where this particular equation will be applicable, that is chi of g is less than or equal to 1 plus delta g. If you want to see that if the values are 1, so this will be the complete graph K2. Here the degrees are equal to 1. So what is the chromatic number of K2? So here the big delta G is equal to 1. So this becomes 1 plus 1, that becomes 2. So if you color this vertex with a label 1, you cannot color the other vertex with the same label. For a proper coloring, it has to be another color which is required. Hence 2 colors are required minimum to color this particular graph. If it is an odd cycle, when k is equal to 2, when k is equal to 2, that becomes odd cycle. Here the degree of this graph is equal to 2. So hence we also call it as k is equal to 2 here in this case. So what is the chi value of K3? This is a complete graph. So this particular vertex can be colored with the label 1 or index 1 of that color. The second vertex, which is adjacent to the previous one, cannot be colored with 1, so another color is required. Third vertex, which is adjacent to other previously given color 1 and 2, cannot be colored with either 1 or 2, hence another color 3 is required. So chi of g is big delta plus 1, that is 2 plus 1, that is 3. So this particular theorem or this particular bound for complete graph and odd cycles, we have seen that it is applicable if the big delta is basically, now we will consider that when big delta of g, which we call it as k, should be greater than or equal to 3 cases only in this particular proof. Now here our aim is to order the vertices so that each has at most k minus 1 lower index neighbors, and then apply the greedy coloring algorithm, which will yield the bound for our discussion. So let us see how we are going to order the vertices, so that this particular condition that at most k minus 1 lower index, it has basically already k minus 1 lower index neighbors, then only we can give a greedy coloring or a k with k number of colors. So let us see the steps in the Brooks theorem. Consider that here the graph G, which is given, is not a regular, is not k regular graph. So what we will be doing? We will choose a vertex of degree less than k. So let us take an example of a graph which is not a k regular. So that means not all vertices are having a degree k in a particular graph. Let us choose this graph and let us have, this is the graph that is called a kite. So it is not a regular k graph. Now here it says that choose a vertex of degree less than k. Here the k is 3, so the vertex with a degree less than k is, let us say, it is Vn, which is degree less than k. Now since this particular graph is connected, so we grow a spanning tree of G from Vn. Let us draw a spanning tree. Assign the indices in the decreasing order as we reach the vertices. So, it is Vn. So, let us say that Vn minus 1, and this is, let us say, Vn minus 2, and this is Vn minus 3. Let us call it as 1, this is 2, this is 3, and this is n. So, let us label it accordingly. So, let us call it as this is V1, V2, V3, V4, V5, and so on up to Vn. So, we say that this particular Vn is here. So, we have obtained the vertex ordering according to the construction of the spanning tree, and then basically from Vn to all other nodes connecting to that particular tree are given a lower indexes. So, this particular ordering we have obtained. So, in this particular graph example, we order Vn minus 3, Vn minus 2, Vn minus 1, and Vn. So, this particular way, if we order, it will follow the following property. So, higher indexed neighbor along this particular path to Vn in this particular tree, here each vertex has at most k minus 1 lower index neighbors. So, let us take Vn. Vn has only one neighbor. So, it is one neighbor on the left side. So, that becomes k minus 2. Vn minus 1 is concerned, it is having 1, 2, 1 and 2. So, it is nothing but k minus 1 lower index neighbors are basically placed on the left side. So, if we apply a greedy coloring in this particular ordering, we can use at most k colors, because k minus 1 colors are already used by the neighbors, that is k minus 1 lower index neighbors, and so basically kth color will be used for that purpose. So, at most k colors will be used here in this particular way. So, if the graph G is not regular, so it will give you the k colors. So, hence chi of G is equal to k colors, that is nothing but big delta of G. In the remaining case, let G is k regular. Suppose first that G has a cut vertex x, and let G prime be the subgraph consisting of the components of G without x. Together with the edges to x, the degree of x in G prime is less than k. So, the method above provides the proper k coloring of G prime by permuting the names of the colors in the subgraph, resulting in this way from the components of G without x, we can make the coloring agree on x to complete a proper k coloring. So, now we will see the cases in this particular way. Now, if let us say that G is k regular, in this particular case we have two different cases further. One is that G has a cut vertex and G is two connected. So, let us take the first case when G is k regular and also has the cut vertex. Now, to see this scenario, let me give you an example graph which will fit in this scenario. So, here this is the example of a 3 regular graph. Now, in this particular, hence it suffices to show that every two connected k regular graph with k is equal to 3 has such a triple V1, V2 and Vn. Choose a vertex x if kappa of g minus x is greater than or equal to 2. Let V1 be x and V2 be the vertices with distance 2 from x. Such a vertex V2 exists because g is regular and is not a complete graph. Let Vn be the common vertex, common neighbor of V1 and V2. Let us take an example graph and understand this particular case. Now, here this particular graph is 2 connected and k regular, and we will consider 3 triples V1, V2 and Vn. Now, choose a particular vertex x. So, here let us say that this is equal to x. Now, if we remove x, so without x, the remaining part of the graph is having connectivity kappa g without x of 2. So, let V1 be x, that we have already assumed, and let V2 be a vertex with a distance 2 from x. So, this particular distance, you see that this is one hop and this is another hop. So, this distance is 2. So, distance of x and V2 here is equal to 2, and we assume a vertex Vn between x and V2. Now, such a vertex exists because this particular graph is regular and is not a complete graph. Hence, Vn is basically be a common neighbor of V1 and V2. Hence, we have shown that in this particular scenario, when the graph is k regular and 2 connected, there exist 3 such triple. Hence, this particular case will also be satisfied with k coloring of the graph. So, k means with the big delta g of a graph. Now, let us see that if there exists, if kappa of g without x is equal to 1. So, let us say that g without x is equal to 1. Let us take another example graph. Now, this particular graph, if we consider without x, so this will be the connectivity of kappa value of this particular graph g without x is equal to 1. So, if x is removed, then basically the connectivity is 1, and let us consider Vn is equal to x. This is another case. Now, since this particular graph g has no cut vertex, so x has the neighbor in every leaf block of g minus x. So, meaning to say that this particular x has basically is a neighbor in every leaf block. So, there are 3 leaf blocks of g minus x. So, neighbors V1 and V2 of x in 2 such blocks are non-adjacent. So V1, so this particular block, they are non-adjacent, that means there exists another such block. Also G minus x V1 and V2, that means if we remove V1, if we remove V2 and if we remove x, the remaining part of this particular graph which is shown here, this part of the graph is G without x, V1 and V2 is connected. Since the blocks have no cut vertices, by the definition you can see the previous videos of blocks. Since the blocks have no cut vertex, that is why removing one vertex from this particular block will not disconnect the blocks. Hence, for k, that is the maximum degree is greater than or equal to 3, that is why this particular x has another, besides V1 and V2 has another neighbor, and therefore G minus V1 and V2 is connected. So that means if x is included, only V1 and V2 are removed, then x will also have a connection with a node, let us say y, because the degree of x in this particular graph is equal to 3. So this is one neighbor with V1, another neighbor with V2, so x is also connected. So hence this shows that G minus V1 and V2 is connected. So we have shown that in this particular scenario also the three triples V1, V2 and Vn, they exist, and thus this proves the Brooks theorem. The bound given by the Brooks theorem can be improved when G has no large cliques. The Brooks theorem implies that the complete graph and the odd cycles are the only k-1 regular k critical graphs. Galai strengthened this by proving that in the subgraphs of k critical graph induced by the vertices of degree k-1, every block is a clique or an odd cycle. So Brooks theorem states that chi of G is less than or equal to the maximum degree of a graph whenever omega G, that is the clique number of a graph, is bounded above by big delta of G, and it is basically at least of 3 degree. So there are various other, Reed has given a conjecture about the chromatic number which is bounded by the average of the trivial upper bound and the lower bound. Now we will see what is the color critical graphs. The graph G with no isolated vertex is color critical if and only if chi of G minus C, that means if we remove an edge from a graph, the chromatic number of that particular graph will reduce, then that graph is called color critical graph. That means it is critical in the sense, it is color critical in the sense that is every edge, if it is removed, it will also reduce the number of colors. Hence such graphs are called color critical graphs. Hence when we prove that a connected graph is color critical, we need only compare it with the subgraphs obtained by deleting a single edge. We will see the proposition, let G be a k critical graph. Now for a vertex V in the vertices, in the set of vertices of a graph G, there is a proper k coloring of a graph in which the color on V appears nowhere else, and other k-1 color appears in the neighbors of that particular vertex. So if that particular vertex is removed, what will happen? The number of, so the chromatic number will also be reduced. Why? Because that color will not be present. So, number of colors will be reduced by 1. Similarly, if an edge is present, so every proper k minus 1 coloring of the graph without that edge gives the same color to the two endpoints of E. Hence, the graph G is k critical, meaning to say that if this is the graph G minus E, if we do the k coloring of G minus E graph, these two vertices are receiving the same color. Hence, chi of G minus E will be chi of G minus 1, because here in G, these two vertices which are having an edge, they may not be having the same color, they may receive the different colors. Hence, this is the proof. So, let us see the proof again. Given a proper k minus 1 colorings of the graph without a particular vertex V, now adding the color k on V alone completes a proper k coloring of a graph. The other colors must all appear in neighbors, since otherwise assigning a missing color to V would complete a proper k minus 1 coloring. If some proper k minus 1 coloring of the graph without that edge E gave distinct colors to the endpoints of E, then adding E would yield a proper k minus 1 coloring of that particular graph G. The graph C5 join Ks is an example of a color critical graph. It is easy to prove using this particular remark and the proposition by considering the cases of an deleted edge E may belong to G or H or have an endpoint at each. In this lecture, we have discussed the Brooks theorem and we have also seen k critical graph. Upcoming lecture will discuss the properties of enumeration in reference to the colorings and also some of the few other topics. Thank you.